Hello and welcome, class, to our final lecture in Chapter 14, wherein today we are going to be discussing reaction mechanisms as well as catalysis. So the following lecture was actually recorded last year in the spring of 2020. This is currently the spring of 2021 during this recording session. So if the audio quality is a little bit different, please understand. In addition, because of the let's say quieter audio quality, I'm going to be removing the background audio, so the lo-fi beats that I tend to have in the background of my lectures for the next few lectures, they will be missing just to make sure that the audio of the lecture itself is a little bit clearer. So yeah, please understand that, and without further ado, let's get started on reaction mechanisms. All right, so what is a reaction mechanism? Well, we have a basic definition of this, but it is what I've already sort of outlined, the idea that a reaction is going to happen stepwise. So we're not going to have one big fell swoop kind of a reaction. It's going to be piece by piece, step by step. And so we can describe this stepwise reaction mechanically in a molecular view, right? So the molecules are going to be coming into contact to cause a chemical reaction, and this chemical reaction can be broken into what we call elementary steps, the definition of which is below. And the mechanism itself is also going to contain a certain number of intermediates, which we also have defined here below. And these concepts are kind of like what you would assume that they're going to be, right? An elementary step is a step that is small. In other words, a single step, right? So we can think of this in terms of like elementary education. If you're in elementary school, you're a little kid, you're taking tiny little baby steps, and that's exactly what this elementary step describes in a reaction mechanism. This is the single step in the chemical reaction. And so if we string all of these steps together, right, step 1, step 2, step 3, there are going to be some molecules that get produced between the final, or the initial and the final stages, and we call these in-betweens intermediates. This is a molecule that's produced during one elementary step, but it then gets used up in a subsequent step. So this is going to be some type of transitional species in between. So let's look at this hypothetical reaction. Let's say that we are looking at this overall reaction where we have two either elemental or molecular species, A and B, coming together to create some final product, D. Well, we can break down what this reaction looks like. Molecularly speaking, we have two A's and two B's. So let's say that A will be this circle that is not colored in, B will be the circle that is colored in, and in order for this reaction to occur, all A, B molecules need to all come together and collide effectively. Well, it's probably not going to happen this way, since four things coming into contact with sufficient energy, molecularly speaking, that's very unlikely. So D, which is going to look a little something like this maybe, is more than likely not going to happen all in one step, right? This is asking a lot. So let's say we could break this down, even just by a single step. At some point after the reaction has began, let's say that we have two A's coming together with a single B to create this intermediate species, C. And so C is going to be the combination of the two A's and the B, this being our first sort of reaction that is occurring. We have the species C probably looking a little something like this. Now, if we want, let's go to blue. Okay, so now I've changed color, so let's look at the second step of the reaction. So we have now our intermediate species C is going to be interacting with B to form our actual desired product, D. And so, despite the fact that I've changed the color, we're still looking at a colored-in sphere here. The second step of the reaction now, where our C is going to come into contact with our D, or C is going to come into contact with B, and this will give us our overall desired product, D. And so here we're getting a description where we're going to break down this reaction into, at least as we have it written, two different steps. We have step 1 and then step 2. And each of these two pieces we would call an elementary step. Step 1 and step 2. This species C we would call a transitional species, or an intermediate, since it gets produced in one of the steps, but then immediately used up again in the subsequent step. All right, so let's look at like the energetics of this. What is it going to look like as this reaction, at least in theory, progresses? Well, a reaction, right, since we're talking about rates, can only ever be as fast as its slowest step. We call this step the rate determining step because this is the step that determines the rate. It is the step that is going to tell us how fast the reaction can possibly occur. Now, the rate determining step is going to be the slowest step. The reason being is you can't be faster than what you are slow, right? If one step, let's say, whichever is the slowest step, takes 1 minute to occur, the overall reaction cannot take place in any time that is less than 1 minute. It cannot happen, hence this little X that I've drawn here. The rate determining step, if that step takes 1 minute, your reaction has to be at least 1 minute long or longer. So this rate determining step is going to tell you exactly at least how fast your reaction can at the very slowest be, since this is the slowest step. Another way to think about this is a chain can only ever be as strong as its weakest link, right? If you have one elementary step that is really, really fast, let's say it takes 1 second, and another step that is really fast, it only takes 2 seconds. And as these elementary steps link together, well, if we have one step that takes 25 minutes, your reaction is more than likely going to end up taking 25 minutes, if not a little bit longer, based on how long all of the rest of these elementary steps take. Now, the rate determining step, how we can figure out which step is the slowest step, on one hand, we can perform any of the number of kinetic studies that we've already done, but if we're going to start tying energy into it, we've already introduced the concept of activation energy, and the rate determining step, or the slowest elementary step, is going to have the largest activation energy. This step, let's say, for example, this 25-minute step, is going to require the largest spark. It's going to require the largest amount of energy to actually get going. These other small steps, these other fast steps, probably don't have a very large activation energy. They don't need very large sparks. And so we can plot this out energetically. If on the right we have this energy, on the y-axis time, on the x-axis sort of plot, let's look at the same hypothetical situation we've looked at before. So our first reaction step was this 2A plus B goes to C intermediate, and then the intermediate got used up interacting with B to create whatever our final product D was. Well, there are two different ways that we can think about this reaction as we have it broken down. Either the first step could be the slow step, or the second step could be the slow step. So what we're going to do is consider both of the scenarios just to lay out what the energetics look like. So either the first step is going to be the slow step, or the second step is going to be the slow step. All right, so let's look at what the energetic map is going to look like if our first step, there, eraser, if our first step is the slow step, there we go, just get that done quick, go back to pen, perfect. So if our first step is the slow step, what this means is that our first step is going to have the largest activation energy, largest EA. And so energetically, wherever our reactants or our products are going to be, let's say reactants are here in terms of energy, so this will be our 2A plus B, and our products, let's say D, are going to be down here somewhere. Well, the reaction takes place in two steps, meaning that they're going to be two sort of humps, two energetic peaks, going from the first step, the reactants, moving energetically into wherever the first kind of round of quote-unquote products are, and from here then, there will be a second little step, right, as the second part of the reaction starts coming together, and eventually we roll into our products, D. So the product of our first step, right, our 2A plus B coming together, is going to be exactly what we have here, our C plus B. Our C was created, this is sort of our first product, and B is still hanging around since the overall chemical reaction requires two B's. We have to have those two B's present. So the C plus B is going to exist in this first little energetic well here. Once these two species react together, giving this second amount of necessary activation energy, however small this will be, eventually these two reactants for the second step will roll into our overall product D. Okay, so the peaks here that we have outlined now, our first peak up above and our second peak, which is slightly smaller, are a representation of the overall energy that's necessary for the reaction to continue. In other words, these are going to be our activation energies. And so we can illustrate the activation energy, since this is the energy that's required for the reaction to progress in these two individual steps. We're going to have two different activation energies. And it's always going to be the difference from the reactant energy here all the way up to the height of the peak. This will be our first activation energy. Now, the second step of the reaction, our reactants are higher in energy, but nonetheless, they are going to require some type of energy put in order for the reaction to progress. But here we can see the difference from the energy of our reactants to to the peak of this energetic requirement is much smaller than the first. In other words, this second activation energy, which I'm going to write as EA2 for the second step, is going to be much smaller than the requirement of the first, meaning that this first step that requires more energy, right, largest activation energy, is going to be the slow step in this illustration. So we're all self-consistent here. Now, once this second bit of energy has been put back into the system, the intermediate product and our last little bit of reactant B are going to react and, boom, release a bunch of energy, giving us our product D. Okay, so how does the energetic diagram look different if we are working with a situation where the second step, let's say hypothetically, is the slowest step? Well, let's look at that situation. So I'm going to erase the curve. If you don't have this drawn in your notes yet, please pause the video now. I am going to get to erasing. All right, so we're going to leave our reactants 2A and B hanging out. We're going to leave our products D here. But now we're kind of flipping the script. We're going to look at the situation where, let's see, go back to pen. Our second step now is going to be the slow step. So this is situation 2. The overall energy then, as we would be able to predict, since now this second step is the slow step, that would mean that the activation energy of this step must be greater than the activation energy from the first step. So let's just draw another hypothetical situation. We would predict that the first activation energy is going to be relatively low, right? Very small. We're going to end up in this small well, just like how we saw before, where there was a peak, a little bit of a dip where the intermediate and our second reactants kind of hanging out, and then, boom, this very large second activation energy can be found here. And if we write in the relative heights of our activation energies again, our first activation energy height is going to be here, little EA1, since this is our first, and our reactant species then, C plus B, kind of exist inside of this little tiny well right here, and the activation energy that's going to, in this situation, require these two things to interact now will be the height difference from the reactants as they exist all the way up to the top of this peak. This is going to give us activation energy 2. And we can see here that EA2 is greater than EA1. That is what is going to signify this second step as being our slow step. So again, everything's all kind of self-consistent here. Now, if in the future we're working with a reaction where we're not quite sure, let's say we have a reaction mechanism, but you are not told which one is the slow step, but if you are given these energetic plots, just by comparing the activation energy of the steps, you will be able to pick out which one is going to be the slow step for that given situation. Okay, so if you have developed any questions at this point, please do not hesitate to let me know. But again, we are going to keep moving forward. So now we have two ideas kind of at our fingertips, right? We have the idea that these reactions can be broken down into smaller steps. We can also describe the connection between the energy requirement for each of these individual steps and how this leads to faster or slower reactions. Again, slow reactions are going to have very high activation energies. This we've talked about already. But we can also connect now the idea that there's going to be a specific step in the reaction that will have the highest activation energy that will determine exactly how fast or how slow the reaction is going to go. Let's look at a reaction not in general terms, but like an actual reaction. Let's look at a hypothetical chemical equation. So the reaction mechanism we can lay out for this reaction below. 2 of our nitrogen dioxides will decompose into 2 nitrogen monoxides and oxygen gases. So this is a very common example for describing reaction mechanisms, since this is a reaction that has been very well studied in the sense of reaction mechanisms, and we have a pretty good idea of how the reaction breaks down and how it takes place. Now again, each of the mechanisms that we can describe for this situation, which we will be drawing in these reaction vessels here, is technically theoretical. We haven't witnessed, like with our eyes, these molecules coming into contact with each other. We can't actually see this with our own eyes, but based on experimental evidence and kinetic evidence and thermodynamic evidence, we have a pretty good idea of what the reaction mechanism is. Okay, so let's start with our first reaction vessel. So we're going to start with our 2 reactants inside of this first vessel, our 2 nitrogen dioxides. So I'm going to illustrate the nitrogen dioxides like so, with our nitrogen being this big kind of sphere, the 2 oxygens being these smaller, darker spheres. All right, and in order for this reaction to take place, right, according to collision theory, we need some type of collision between steps 1 and steps 2. So assuming that these 2 molecules have moved together, that they have come into contact with sufficient energy, sufficient activation energy for step 1, the 2 molecules, from what we can theoretically postulate, are going to break down like so. One of the oxygens from the first molecule actually shifts onto the second molecule. So we have this oxygen from our first nitrogen dioxide moving over in this collision onto our second, what was previously a nitrogen dioxide. Now we are left with NO and NO3. We can see that one of these NOs is one of our desired products. Yay, we have one of our products already. And so the second step of this reaction that we've been able to theoretically kind of gather is that this NO3 molecule here, which this is not a nitrite, there is no charge here, this NO3 in its neutral form is actually a very unstable molecule, and so it will decompose. This decomposition reaction is going to have its own, again, associated activation energy. It will have its own second step requirement, but as the molecule then will rearrange and break down, the oxygens here will kind of move their way together, and so overall we'll be left with our nitrogen monoxide that's already been produced, another nitrogen monoxide that will be left over. We can kind of see here there is a nitrogen and an oxygen, and then our 2 leftover oxygen molecules will come together. So here we have a description sort of laid out for how activation energy kind of pairs along with the physical nature of this reaction, and how, yes, we could, in theory, say that these 2 nitrogen dioxides will come into contact in this whole shuffle, this whole collision and decomposition will happen all in one step. Theoretically, that's possible, but it doesn't line up with what we've experimentally seen. Experimentally, we are able to witness the production of this NO3, which, yes, is unstable, but it's just stable enough that we can see it spectroscopically. And so we have evidence for this NO3 being produced before everything breaks down into NO and O2. So how does this tie together quantitatively with the conversations that we've had before? Right, we've just laid out the idea of a reaction mechanism, we have our elementary steps, we have our rate determining step ideology in terms of the activation energy, but how can we predict quantitatively what the reaction rates are going to be? So what we're going to do here is tie together the idea of our elementary steps with the rate law expressions that we've talked about before. So the rate orders, as we've sort of witnessed in the rate law expressions prior to, we've seen some cases where a reaction, let's say the decomposition of ClO, goes into whatever its products are. There is a coefficient of 2 here. And the question was asked in class. I forget who asked it. Well, this reaction we were looking at, we were told it was a second order reaction. Does this coefficient of 2 out in front mean that we're working with a second order reaction? And the answer I gave was technically not quite. A lot of the time it's true, but most of the time it's not. There's actually a deeper underlying reason, and it has to do with our elementary steps. So that's going to be what we talk about down here. The rate orders in the rate law expression are equal to the stoichiometric coefficients of a given reaction or reactant, but not for the overall reaction, only for an elementary step. So let's look at an example. Okay, let's look at the reaction that we just broke down. So we have our overall reaction of the two nitrogen dioxides breaking into two different nitrogen monoxides and an oxygen gas. And here were the two that, proposed steps that we laid out, right? Step 1 and step 2. The first was the collision of the nitrogen dioxide molecules together, giving us a nitrogen monoxide and a nitrogen trioxide NO3 intermediate species. This intermediate, then we said, which is step 2, decomposes into our two other products. The rate law expression that we can write for each of these two steps is going to follow the rule that we've just laid out. So the rate for both of these reactions is going to be equal to some rate constant K, right? That's always going to be involved wherever we're writing a rate law expression. We always have rate constant K multiplied by our reactants. Now in the first step, the reactants, we have two different NO2s. We only have one concentration measured, though, for those NO2s, but because there is a coefficient of 2 here, that means that in the rate law expression, we're going to square the concentration of the NO2. So this is where the stoichiometric coefficient is coming into play. If we've broken down our elementary steps, we can move this exponent, or the stoichiometric coefficient, into the exponent of 2 here. The next reaction, we can see that we have an intermediate species present as the reactant for our second step. And so we have the second rate constant for our second step. Let's even give them little subscripts so they're kind of distinct from one another. So step 1 has its own rate constant, step 2 has its own rate constant. Since these are two different reactions, makes sense that they would have their own different kind of energetic requirements. Again, our rate constants are where the activation energies are found in this expression. So there is no stoichiometric coefficient, or rather there's a coefficient of 1 implicitly here, so we're going to raise this concentration of NO3 to the 1. Now, experimentally determined rate law expressions are going to match that of whatever the slow step is going to be. So what I mean here is that if we want to validate a reaction mechanism, in other words, like how do we know that this proposed mechanism, this theoretical mechanism, is true? Well, I did say that there is experimental evidence for this, and so here's how we can validate this type of reaction mechanism. So if your rate law expression of your proposed rate determining or slow step matches an experimentally determined rate law expression, then you have a good to go reaction mechanism. It has been validated, and what that means, what this validation means, is that it is your reaction mechanism is experimentally supported. Okay, so the overall reaction that we've been talking about, this nitrogen dioxide combining together to give us two nitrogen monoxide and an oxygen gas, has experimentally been found to have the rate law expression provided here. The rate is known to be equal to a rate constant K times the concentration of NO2 squared. This should be an NO2 squared here. The rate law expression that has been experimentally determined, just to go backwards a slide, matches that of one of our steps. It matches one of the steps because we can say that this is the slow step. This first step is the rate determining step. And if we were going to compare this ideologically, then step 1 requires two molecules to come into contact with each other. This is going to take time. Our second step is a decomposition of an already unstable molecule that doesn't require on any other, or doesn't it moving forward, this reaction moving forward, does not require any type of collision or timed event. It is just this molecule decomposing on its own time if it has the energy to do so. And so we would expect this second reaction, the second step of the overall reaction, to be faster since it doesn't require any other factors to move forward. This first step is going to be the slow step. And so whatever happens after this first step, after this first elementary proposed step, is going to occur faster. But the overall rate is going to be dependent on this weakest link, this collision requirement. Energetically, we can break down what this is going to look like in just the same way that we did before with our kind of hypothetical sense. We have our two different reactants, or in this case, two of the same reactant, or two NO molecules coming together. We would predict then, over the course of this reaction, since we've just established, based on this experimental knowledge, that yes, I didn't work through this, but we can or could work through an initial rate law sort of problem that we've learned before to figure this out. So right now I'm just kind of taking it on a, take my word for it sort of approach, but this is the experimentally found rate law expression for our overall reaction. And so we would be able to predict, based on the mechanism that we just proposed, which lines up with experimental data, that this NO2 is going to take a lot of energy in the first step to come together and break down. After this first step is finished, the second step will take less required energy in order then to turn into our overall desired products, the 2NO plus O2. And so in this in-between, this is going to be where we have one of our NOs present already, but we are left also with an NO3 that must decompose to give us our final product. The activation energy, just to make sure, again, everything is aligned, the activation energy of the first step we would expect to be greater than the activation energy of the second step, since this first step is, again, the slow step. And we can see that the second activation energy is definitely smaller than the first in this hypothetical drawing. We could put some specific numbers to it, but the overall idea is that our first activation energy will be greater than our second activation energy. Specifics need not really apply in this kind of hypothetical that we're looking at. We're still just laying out the ideas. Okay, so there is one flaw, or at least something unexplained at this point. So if we go backwards again, and we're looking at the overall proposed reactions, the overall steps, I didn't really address this rate law expression, which does have a little bit of an issue with it. And the reason that there's an issue is that we have some type of intermediate present here. And technically, we can't have an intermediate somewhere in a rate law expression. And the reason is we don't measure the intermediate before we start, right? There's no concentration of NO3 that we can measure or calculate when we first start the reaction. We're always looking for initial rates and initial concentrations, and there is no initial concentration, right? No NO3 initially to measure a concentration of. And so what we need to do is figure out a way to rewrite this rate law expression. Since the NO3 is produced in the first step, we want to find a way to rewrite this that is going to be based on some initial measurements here. So what we're going to do is not necessarily that for the specific problem we've been working with, but let's say a different hypothetical. Since in the first example that we've looked at, the first step is the slow step, whatever the rate law expression of our fast step is, it doesn't really matter. The case where it is going to matter is when step 2 is your slow step. Here's where we're going to start caring about what is the rate law expression and does it contain an intermediate. So let's look at, assuming the proposed mechanism below has been validated, so the overall reaction mechanism, let's say we're going back to that first hypothetical we looked at, we have two A's and a B coming together to make a C, and then a B and a C coming together to make a D. Let's say the first step was the fast step. Step 2 is the slow step. So if we go all the way back to that ideologically, we're going to be looking at this kind of a scenario. The first step is very small. The second step is going to be very large in terms of an energetic requirement. Okay, so I'm going to move back forward here. Now we can write out some rate law expressions for these two proposed mechanisms. Now before I write anything down, I would definitely invite you to kind of pause the video, sort of like munch over what we've been talking about so far, and see if you can't write these rate law expressions for the elementary steps based on the example that we just talked about, right? We have our initial reactants here. We have their stoichiometric coefficients out in front, whether they be explicitly written or implicitly written. Definitely take the moment, pause the video, see if you can't write out these rate law expressions for yourself. Now, assuming that you've paused the video there and actually did that, or not, I'm going to keep going, but let's see if your answers then line up with what I wrote or will write down in a second here. So the rate law expression, again, as always, rate is equal to some rate constant k. And again, I'm going to have a subscript of 1 and a subscript of 2 since these are steps 1 and steps 2. And the rate constant k is going to be multiplied by each of our reactants. In this case, we have reactant A and reactant B. And the A and the B will be raised up to the stoichiometric coefficients that they have in front of them in our overall chemical equation. And again, this process is only true if we are working with reaction mechanisms and the concept of our elementary steps. We cannot do this for an overall chemical equation for the reasons that we are about to state or about to go into, specifically for the scenarios when our second step is our slow step. Okay, so step 2, we have a reactant B and a reactant C. Now this B and C are also going to be multiplied together. Their stoichiometric coefficients are both 1s, so we can have little implicit 1s up here, but ultimately the rate is going to be equal to our second rate constant multiplied by the concentration of B and the concentration of C initially. All right, but as I just said, or at least introduced the idea of, our hypothetical reaction here, where the second step is the slow step, has an intermediate in our rate. But this is not a reactant that we can actually measure at the start of the reaction to get an accurate prediction as to what our reaction rate initially is going to be. So how can we work with this idea? How can we, let's say, substitute or solve for what this reactant C is going to be equal to? Okay, so the overall energy is going to give us a clue here for what it is that we're going to be doing. So if our energetic landscape looks a little something like this, where our first step is going to be very slow, or very small first activation energy, and our second step is going to have this very large activation energy. Well, as we are starting with this low energy state for the reactants, regardless as to how much energy the second step is going to take, we can almost imagine as we are increasing the energy of the reactant system, let's say we increase the energy to here. We've put in this much energy so far, whether it be from heating or stirring. We can almost imagine a situation where the 2A plus B going to C plus B, if we've added this much energy already, well, we have 2A plus B is going to be overcoming this first activation energy to create C plus B. But if we don't have enough energy to really push C plus B all the way down to our final product, it also makes sense that if we're still increasing the energy, that C plus B, energetically speaking, could go backwards. That C plus B could react together. Since this activation energy requirement is definitely met, this reaction can go backwards with some ease. In other words, if the second step is the slow step, which that is the case here, this is our slow step, this first step is reversible. This first step, as we are increasing the energy of our overall system, is going to be able to move forwards from our initial reactants to products, which include the intermediate, but this intermediate can also move backwards to reactant. And so what this is going to give us is a means to calculate what our overall rate law expression is going to be. So how we connect this all to our reaction, our rate law expressions. How do we connect the reaction mechanism to the rate law expression? Well, the first step that we wrote out as was step 1, which now we're going to label as in the forward direction, had a rate that was equal to K1 times A squared times B. But we just said that this reaction, this first step of the reaction as it moves forward, can also move backward. So this reverse reaction, where now we have C specifically breaking back down, right, because C is the creation of A plus B, we now have this C breaking down backwards, the C decomposing back into the initial reactants. So this new reaction, this backwards reaction, can be written as C decomposing back into 2A and B, and the step 1 rate law expression in reverse is going to be equal to rate is equal to K1, and I'm going to add a little R here for reverse, times concentration of C. Ooh, 2 concentrations. Silly me. Let's erase that quick. Don't need a second bracket. Boom. Okay, so the first step can be broken down into 2 smaller steps, which is exactly what I did here. The second step, which is our slow step, step 2, is going to have the exact same rate law expression. Rate is equal to K2 times B times C, concentrations of. But now what we've done in breaking down step 1 into a forward and reverse is give us a way to solve for the concentration of C as is dependent on A and B. So let's look at how we can do that. Well, what's important to recognize, and this is going to be something that we really get into in the next chapter, chapter 15, is that if a reaction is able to move forwards and backwards, assuming that the reaction is stable in doing so, that A and B are going to be reacting together, C decomposing as this energetic threshold increases, the rates of these two are going to be equal. The rate of the forward will be equal to the rate of the reverse. So if these two are equal, right, if A is equal to B and A is equal to C, well then we can set these two right-hand sides of the equations equal to each other so long as the two rates here are equal. Now, if the first step is the fast step, we're going to make this assumption that these two rates will be equal. And what this means is that we can set K1, concentration of A squared, times concentration of B, equal to the rate constant of the reverse decomposition times concentration of C. And here we can rearrange and solve for the concentration of C, since this is what we want to solve for. Again, we're trying to find a way to remove concentration of C, this concentration of an intermediate species, from the second piece here. So the reaction here, or the equation here, we can rearrange to solve for C by dividing each side by the rate constant of the reverse, canceling these out, giving us a concentration of C that is equal to the rate constant 1 times A squared times B, all divided by the rate constant of the first step reversed. Now these two numbers will end up being different since we are again looking at two different reactions. In the first case, we're looking at a combination reaction. In the second, we're looking at a decomposition reaction. So it is going to be important to label these K's separately. This K will not disappear. This whole term is now equal to the concentration of our intermediate. In other words, if we know the rate constant of the forward and the reverse reactions, and we know the concentration of A and the concentration of B initially, well, now we can substitute this in to find a concentration of our intermediate C here in the overall rate law expression. All right, so just to clean up real quick so we can rewrite. Again, if you haven't written down this math that I have written, please do so now, like pause the video to do so, and I'm just going to start erasing. Okay, so the overall then rate expression for the reaction, since this second step is the slow step and this is what we want, our rate is going to be equal to K2 times our initial concentration of B times everything that we just solved for. So this is going to be K1, all divided by K1 in reverse times concentration of A squared times concentration of B. Now this looks terrible. It looks awful. So what we're going to do is simplify. We're going to lump all of our K's, all of our rate constants together. Since we have them each individually labeled according to what step they all kind of go along with, we're going to lump all of these together, and our K, our rate law constant overall, is going to be equal to K2 times K1, all divided by K1 in reverse. So this is going to be the first substitution that we're going to make, or rather, in this case now, the last substitution we're going to make. So the overall rate is going to be equal to our rate constant K, which is lumping all of these other K's together, times A squared times B squared, right? Since we have a concentration of A squared here. And we can multiply these two concentration of B's together. Since they are the same value, we can write all of them together like so. And now we have a way to calculate what our overall rate of the reaction is going to be, assuming that our reaction mechanism is correct, and step 2 is our slow step. So yes, it's tedious. Yes, we're making some assumptions here, but this is going to be the best way to solve for what our rate law expression for a reaction in which the second step is our slow step is going to be. Okay, so how does all of what we have talked about so far connect to catalysts? This is a concept that we introduced back in, oh man, it was like day 1 of kinetics. So whenever we started kinetics, definitely feel free to go back into your notes. What we had described catalysts before as were these, at least in terms of enzymes, I think it's a really good example, as a catalyst, as a protein or a large molecule or some type of reactant you can add to a reaction to force your two reactants, let's say A and B, to come into contact with each other and react via our description of collision theory. All right, but how a catalyst actually works is also tied to the discussion that we've been having now. So the discussion of taking a reaction, breaking it down into steps, a stepwise piece or a series of stepwise pieces made of elementary steps, each with their own smaller activation energies. And so a catalyst we can describe, like with a technical definition, I'll be tying the physical and the energetic pieces together in a moment. A catalyst is a substance that is added to a reaction. So it is going to be listed, if we're going to, keep using the previous example we've worked with, a catalyst is going to be added to a reaction. We can either write this catalyst over the reaction arrow like so, going to product D, or we can write it 2A plus 2B plus catalyst. C is already taken, D is already taken. So let's go with G. G will represent our catalyst. Okay, so we can add G to the reactant side of the reaction as well, but what's going to be important is that as the reaction continues, we are going to not only have product D, but also catalyst G will come back to us. Because a catalyst is going to be added to a reaction, but if we jump ahead in the definition, it is also not consumed in the process of the reaction. Catalysts are special in that way. They can be added to a reaction to make it happen faster, but they don't get used up. They are not turned into any type of new product. And so for that reason, we oftentimes, again, don't have the catalyst present inside the reaction. It is going to be written over the reaction arrow, catalyst, G, if we're going to stick with this consistent kind of self-description. This is going to be different than a transitional species like C, since C is not a reactant, right? That's the major difference here. A catalyst ultimately gets used up and then brought back. It's not used up totally in the process, whereas a transitional species is produced at some point in the reaction and then used up in a subsequent step. So that's the difference between the two. Okay, but how does a catalyst work? Well, if we return back to our definition, a catalyst is going to work. It increases the rate of reaction by lowering the activation energy. So again, catalysts, it's not just about the physical mechanics of how they work, it's also about the energetic mechanics of how they work. Okay, so in this chart here, there's actually a typo. This should not be energy, this should be time. So if we look at a plot of energy versus time as reactants, move to product, if there were no catalyst, and if the reaction only took one step, because that does happen sometimes. It just doesn't happen all the time. If a reaction happens in one fell swoop going from reactants to products, we can say that the reaction is going to take place in one step, as is energetically illustrated here, with a relatively large activation energy. And when I say relatively, I mean compared to this blue curve. So what does the blue curve represent? Well, this is the energetic curve of what happens when a catalyst is added. What we've been able to find experimentally is not just that a catalyst lowers the activation energy of your overall reaction, but it actually breaks your reaction down further into, as we can see energetically here, 1, 2 different steps. Now, some catalysts break your reaction down into 3 steps, some break your reaction down into 4, some even more than that. But what a catalyst does is it causes your reaction now to break down into 2 smaller pieces. And if we're looking at the overall number of tasks that need to get done, chemically speaking, it's not as important as the energy associated with the number of steps that we have. So, in other words, step 1 and step 2, yes, we have a greater number of steps, but they require less energy to be put into the reactants than if we didn't have a catalyst at all. So we would only have to stir or heat up the reaction so much, let's say heating or stirring. If we trace this kind of sideways over here, we would only have to heat it up like half as much as what we would have to if we didn't have the catalyst present. And so if we insert enough energy, yes, this first step is going to be slightly higher in energy than the second step with the catalyst, but once we've heated the system up adequately to overcome this first little activation energy, boom, boom, the reaction is going to be done. This first step in the scenario with the catalyst will be your slow step, but it's still going to be faster than if you didn't have a catalyst at all. How many steps a catalyst is going to break your reaction down into is going to depend completely on not only the catalyst, but also the reactants that the catalyst is working with. For that reason, I would not expect you to be able to predict exactly how many steps a reaction is going to break down into, but you do have the ability to be able to describe in general sense, yes, a catalyst will break down a reaction down into smaller steps, and those smaller steps will have lower activation energies. There are, though, 2 main classes of catalysts, and this is going to be where we end it, just the description of these catalysts. The first type of catalyst is a homogeneous catalyst. This is a catalyst that is going to be in the same phase as your reacting species. So in other words, we have this really common or famous catalyst that is illustrated here. It is ruthenium tris-bipyridine, also known as rubipi. I'm not making that up. Every scientist I know calls this thing rubipi. It is this beautiful red color, and if it's in its solid form. But what's awesome about this is that it is totally soluble in aqueous solution. It's totally soluble in H2O. So this is a catalyst that is actually added to a lot of photovoltaic reactions. Photovoltaic meaning that we're looking at the relationship between light and electricity. So this catalyst is very useful in being able to speed up like semiconductor or solar cell or photovoltaic types of reactions. It's very, very photosensitive. The problem with rubipi, like the reason why you might not hear of this being in association with like solar cells or semiconductors, is that ruthenium is incredibly expensive and there's not a lot of it. So there's actually very active work right now being done in trying to find a replacement for the ruthenium in rubipi that is going to be not only economically cheaper, but let's say chemically cheaper. Something like iron, something like iron oxide, so the iron 2 oxide, or even iron 3 plus oxide. In other words, rust. Like, would there be a way to turn rust into a solar cell? There's work being done right now. The answer currently is no, but we do have some really promising leads in how we can take something like iron or nickel or cobalt, which are considerably cheaper and more abundant in the earth than ruthenium, and taking them and turning them into something useful for us. All right, the other type of a catalyst then, right, if we have homogeneous, we also must have heterogeneous. Heterogeneous catalysts are going to be catalysts that are not in the same phase not in the same phase as your reacting species. So a very common heterogeneous catalyst is going to be platinum. If you just take solid platinum, which is represented by this kind of flat sheet here, this metal surface, platinum is very good at being sort of like a rough surface for hydrogen to come down onto and break down into H+. This type of system is one that you will be working with in organic chemistry. There are a lot of really neat catalysts in organic chemistry, a lot of them heterogeneous, that help hydrogen to break down and then possibly also recombine with carbon. So what we have here is ethylene. This is carbon with double bond between it, 2 hydrogens off of either of the carbons. Ethylene can come in on this reaction, as we can see here, reaction arrow coming in, and the product of these two H pluses and the ethylene coming together is going to be ethane. This reaction is also one that is like very well known in catalysis. It's very well studied, and again, you will be looking at it possibly in organic chemistry for this type of hydrocarbon, reactivity. But that is all we have to discuss today. So that is reaction mechanisms as well as catalysis, at least insofar as we're going to be talking about here in general chemistry. So here we have some suggested problems for you pertaining to reaction mechanisms, checking out the validation process, that good stuff from lecture today. Otherwise, though, please double check and do your homework if you have any homework. If you have any questions, don't hesitate to reach out. And until next time, class is dismissed.